How are you guys? Good? Tired? I don't know. Something about today. I woke up and I'm just tired. It's that late October, early November tiredness. You guys probably have it more than me because you guys have, of course, a ton of midterms. But we're almost at reading week, right? This close. This close. You guys going to do anything fun over reading week? No. What are you guys going to do over reading week? Study, study, study. See, it's funny because every time I ask that before reading week, study, catch up on assignments, do some labs, and then I'm going to ask the same question after reading week, and I slept. It's good to have those good intentions heading into it, but reading week is designed for you guys to take care of yourselves, have some fun, relax. So please do that. Please, please do that. Do you guys think you're going to have to do 398 over reading week? What do you guys think? Well, I'm not sure. I'm curious. We'll be done our midterm, so I'm hoping you're not studying for a midterm. You have bigger problems. The day you get back, is that 374? Yeah. 381. Has that gotten fun yet? You guys enjoying 381? You guys notice that if you guys got to the point in 381 where you're finding the stress on soil, and to do that you have to subtract the hydrostatic stress? Isn't that what we did with the deviatoric and hydrostatic stress? Oh, isn't it related? Think about it. I said that hydrostatic stress, does it cause shear? No. We said that that's why we subtract our hydrostatic stress to get our deviatoric stress. Our deviatoric stress is actually just a function of the von Mises stress and vice versa. Remember, the von Mises stress is what we use to determine if things fail. So if that deviatoric thing is based on stress, and that's what you guys are doing at 398, when you guys are analyzing soil, aren't you looking for those planes in which the soil shears? It's the exact same thing. That's why I love this class, is everyone sleeps on this class. They think, it's just a bunch of math. Who cares? I know that because that's what I thought. I came out of this class. So I took it. I was here. I was with Sam. I had no idea what was going on. I'll be honest with you guys. I'm not going to come here and say that this was the most important class of my undergrad. This was the least important class of my undergrad because Dr. Sammer had those assignments and midterms so easy. He'd give us all the Mathematica code. Half of the midterm questions were from previous midterms, and it was open book. This class, when I took undergrad, didn't really mean a lot. But looking back, you realize that everything you guys do, soil, fluid, structural, starts here. All that theory starts here. Today is going to be a great example. Euler-Bernoulli beams. I haven't taught it to you guys yet. But have you guys heard of these before? Yes. This right here is going to form the basis of all of structural. All of structural. I'm getting too excited into the lecture. I want to talk about reading week. Is there anything I can do, me, to make your reading week easier? I can't. If you guys have suggestions, put up your hand. I will do anything to make your reading week easier. Reading week should be for you guys. It shouldn't be trying to catch up. I know that's what it turns into at the very end of it, but make sure you guys are taking time for yourselves. That's the number one most important thing. Stress, strain, who cares? The stress on yourself. That's what matters, okay? So make sure you guys take that time for yourselves. For those of you guys are in that fun spot right now, where it's kind of your last hard year. What do you mean by that, Clay? What do you mean? Isn't next year going to be hard? Next year is when you take kind of your final classes. And then you guys will be engineers. Then you guys will be designing, having fun in the real world. But most importantly, getting paid. Doesn't that sound nice? Getting that nice fat paycheck every 2 weeks? Yeah. You guys are almost there. Next year, it's a piece of cake. Next year, you'll find that the homework load goes down. You'll find that the midterms are easier. And then by the end, you'll not even care about the midterms. That's the best part. Midterms and finals in your final semester when you already have a job lined up? Well, who cares? All you need to do is pass. You already got a job. You did what you came to school for. Who cares? My lowest mark in my third and fourth year, my second lowest mark was A minus. What was that in? I forget. I know it was A minus. Second lowest mark. Guess what my lowest mark was? A C. What? What class destroyed me? Take a guess. Not really destroyed me, but I just didn't care. No, it wasn't a civic class. Eng law. You guys taken Eng law yet? No. I don't know. Well, it was 8 a.m. and I didn't show up, so maybe it was on me. But I remember sitting in that exam, and it was right after you got the iron ring. So I was just sitting there like, I don't really care who wins this court case, because I already got what I came here for. So relax. You guys are all doing fine. All right, I've seen your grades. Trust me, I know. Clayton, how can you tell if I'm fine? I know your grades. A lot of students were surprised that I can see every single one of your attempts also on the assignments. Every single one. So basically 90% of you just enter 0 for the first attempt, find the answers, work backwards. But no, because at the end of the day, at least you're trying the assignment. I'd rather you guys do that than just ask a friend for the answer, throw it in and leave it. I feel like at least you guys are somewhat learning. At least I'm hoping so anyway. Which will lead me to my question. In this class, do you think that you've taken something away from it? You can say, no, I'm not going to have my feelings hurt. Or just a little bit. So what do you think? Have you guys learned something useful in this class? All right. Not really anybody? Is class a waste of time? Has to be one of the two. You guys are always too funny. So the whole point of this, relax, have fun. You're supposed to have fun. You guys will graduate before you know it. Trust me, you'll be walking that stage. Well, if COVID ends. Otherwise, you guys will be watching that stage through Zoom. And you guys are going to look back and say, wow, I wish I had more fun in undergrad. Trust me. That's what you guys will be thinking. You won't care about what you got on assignment 5 of 398. You care about having fun. That's what you guys are young adults. Have fun. Okay? Be responsible, but have fun. All right. So we're going to talk about the midterm first really quick. Midterm 2 next week. 25 multiple choice questions. It starts at 8 o'clock, ends at 9:20. Same thing as before. Same format, same question types. And it's going to focus from strain all the way to constitutive laws. Are we going to test Euler-Bernoulli beams? No. This is now, what, topic 7? I'm not too sure. Everything that we learned today, as well as on Tuesday, not on the midterm. It's just going to be strains, stresses, momentum balance, and constitutive laws. Those 4. The question I always get, and this one sucks to answer, is it cumulative? Do I need to worry about what we learned at the beginning of the course? Well, technically, no, it's not cumulative. Every question will be stress, strain, momentum balance, or constitutive laws. But if I ask you guys for something like principal stresses, how do we calculate principal stresses? Eigenvalues. When did we learn that? Beginning of the course. So it's one of those things that I will not directly be testing that linear algebra, but will you need it to stress and strains? Yes. So I'm hoping that answers most questions. Do you guys have any questions for me about the midterm coming up? Again, next week, 1 week from now, right before reading week. Yes? Review sessions. Great question. So I'm going to have 2 review sessions. They're going to be Monday and Tuesday next week, and I think I have them starting at 5 o'clock. So I think that's what I had before, 5 o'clock. 5 to maybe 7. It usually takes around 2 hours, or I'm not sure how long the first one took. But on Monday, we're going to go over 2014. On Tuesday, we're going to cover 2015. Sound good to everybody? Yes.
Are they going to be recorded?
Yes. It'll be just like the first one. It'll all be recorded. It will all be uploaded because I know I say 5 o'clock thinking most of you guys are free. Reality is probably half you guys are not free. So of course, I would never do that to you guys. That would just be too mean. Any other questions? Maybe I hold it ransom. I'm thinking about doing that to the Eng 130 kids. I have a midterm session for them today. And I'm thinking, well, hey, you guys want a final review session? My subscribers could use a little bit of work. We'll see how I'm feeling. I'm still salty because I had to create a new account, but that's a different story. You, Alberta, getting me good. All right, so midterms covered. Reading week, you guys are going to be happy during reading week? Does anybody have anything fun planned for reading week? Not a single thing? Wow, that's sad. Plan something. Have some fun. I know travel's kind of out the window, but there must be something. Lego's coming out. Home Alone set? Who wants the Home Alone set? No? No one knows what I'm talking about? You guys seen the Titanic set? Oh, that's my reading week. Well, it comes out at the end of reading week, of course, so kind of my reading week. Animal Crossing update, anybody? No? What do you guys do? I know I have a very limited window between video games and Lego, but you guys must have something. No? Sports? Watch the Oilers blow another lead? No? No? Toronto? Well, if you're a Toronto fan, just don't watch them. That's just going to make you depressed. So no sports either? Come on, guys. Must be something. Don't make me pick on you. Oh, yeah. What do you do for fun? Yeah. Find something fun. Find a hobby. 398 is your hobby. Don't. It'll ruin you. This is the fun stuff. Remember how I always talk about in design, how we learn the simple stuff. In real life, it's a whole different game. That's the same for this course. This is just a fun, easy peasy, how you doing? Turns out this is actually disgusting. That's why I like teaching it, because I find it disgusting, and when most profs teach it, it's disgusting. So I like the challenge of showing you guys it in hopefully an easy to understand way. I took the graduate class from the Mechie department of Continuum mechanics. Oh, yucky. Yucky, yucky. So don't let this be your hobby. You guys can have any hobby except for this. It'll ruin you. I want you guys to have fun. This is not fun. So find fun hobbies. Okay? That's your homework over reading week. Find a fun hobby. I will test you. I have the power to test you to make sure. All right, so hopefully I got everything covered. Office hours today, 10 to 12, those are still a go. I might be a little bit late, so I have to go grab food. Usually I grab food at 12 when they're over, but we have a faculty meeting today, so fortunately not. Any messages you want me to give the other profs? Too funny. All right. So today, Euler-Bernoulli beams. Let's actually start the lecture. Midterm 2, those topics were very important to us. I talked a lot about this in our seminar. I didn't do it on the online seminar, but I talked a lot in person. I said all those topics that we have, even though we separated them into 4 components, they were all very much related. Very much related. Because what we would do is we would take displacement functions and we would find strain. That was kind of topic number 1. From there, we said, okay, if we know strains, can we find stresses? What do you guys think? If I know strains and I know what type of material we have, can I find the stresses? Yes. And if I know the stresses, my Cauchy stress tensor, 3x3, can I find things like the von Mises stress, maximum shear stress, things like that? Yes. And then can I compare that to limits to determine if things failed? Yes. I already talked about it in the seminar, but that is every single design software out there. It takes displacement functions, it finds the strains, it finds the stresses, and then it compares them to whatever limits you guys set. Now, the one thing that you guys have to keep in mind about software, and this is one of those little disclaimers, is that it will never tell you if it failed. If I were to go into a finite element software, one of them is Abacus, we're going to talk about it at the end. and I were to define a material, and I were to say the yield stress is 400. What's going to happen in the simulation is it's going to go up as I apply the load, but once it hits 400, it's not going to say, hey, Clayton, this failed because it yielded. It's going to stop at 400 and just continue on. So the software is not going to quit. It's not going to say something failed. But when I actually look at the results, I'm going to see my stress increase. It's going to hit 400 and it's going to stay the same. So that's one of the major things about this course. It's not so much also just determining the steps that a software would take. It's determining those failure modes. If you guys see that the stress is 400 and it stays 400, can you say that it's yielding? What do you guys think? What's going to happen is the software will give you a nice contour plot of the von Mises stress at every point in your structure. If one of those points is 400 and you set that the yield limit was 400, can you say that location is yielding? Yes, you can. You know that yielding is 400. The software says it's 400, but again, the software won't fail. That's another thing too that we didn't talk about. Think about your design class. I know those in 372 can't relate, but think about beams. You guys design beams that they yield when they fail, right? You compare that to the moment. Is the moment the same at every point in the beam? So when you have a structure, is everything just suddenly going to all yield at once everywhere? No. Some spots are going to yield, and then it's going to yield further throughout the beam. That's one of the nice things about software, and that's why it doesn't just stop when first yield hits, because there's still additional parts of the structure that can still take on load. So it's one of those very important things. I want you guys to keep that in mind. But back to the fun of it, that process that we had, displacement, strain, stress, failure, we started with displacement. Up until this point, I've always given you displacement functions. Always. I've either given you displacement or position functions. In reality, let's take 374. Are you given the displacement function of a beam when you go to design it? No. What are you given when you design a beam? What are you given when you design a beam? You're given material properties, yes, but I heard it in the back, loads. Loads is where everything starts. It doesn't start at displacement, it starts at loads. And this is true. In design, will you always know the loads? What do you think? Well, I will always know my loads when I design. What do you guys think? Yes or no? Who thinks yes? All right. Some. Who thinks no? Okay. It's kind of in between. The majority, yes, you will know the loads. When I design this slab above us, all of my loads come from the National Building Code of Canada. All of them. If you go to the States, they have their own building code. But if you look in the building code, it'll say something like you have a lecture hall with a capacity of 400. The live load is 1.5 kPa. The dead load is 2.5 kPa. All the loads come from the building code. The only scenario where you're not actually given loads is earthquakes. Why do you think we don't know the load in earthquakes? What is an earthquake? Dynamic event. But what does it do to our structure? Again, I don't expect you guys to know this because it's outside the scope, but it's fun to learn. It's an acceleration. It's a shaking. That's what happens at the bottom of the building. What is the definition of force? Force is equal to what, according to Newton? An earthquake is acceleration. So if I want to know the force of an earthquake, it's just mass times acceleration. I take the acceleration of the earthquake and multiply it by the mass of the building. Isn't that great? That tells us one key thing. If the mass of my building is very, very low, are my earthquake forces going to be very high? No. So you can have a devastating earthquake, but if I have a simple structure, who cares? This is why you guys don't really see houses impacted too much during earthquakes. It doesn't have a lot of mass. Wood is very, very light compared to the other materials. So there's no real forces. When you start getting into high-rise buildings, that's where things become a problem because there's a lot of mass, a lot of earthquake forces. The other problem is this. If I'm designing, let's say that this was my building, and my forces from an earthquake act at the bottom. Is this just a cantilever beam? So is there going to be a lot of moment? Yes. So that's the problem with high-rise buildings. First of all, it has a lot of mass, so it's going to take a lot of earthquake forces. The second thing is it's a big cantilever with the load at the very base. So it's going to start shaking like crazy. It's one of those really fun things. But the point is, for the most part, we know forces when we design. If you guys look at one of your 372 questions or one of your 374 questions, they usually give you a beam, they give you a distributed load, some reactions, and then they ask you for whatever they want. The question is can we take that exact same scenario where I just give you a beam with some loads, and I say, tell me the stresses and strains? The answer is yes. Is it going to be messy? Who thinks it's going to be a messy procedure? One person? Not bad. The answer is no. It's actually going to be quite simple. Clayton, why? Because we make a lot of assumptions. Right? Isn't that all of engineering, making assumptions? Those of you in 374, I've already talked about this. Do you guys use Poisson's ratio? One of the assumptions is we ignore it. Isn't that great? All that stuff we just learned last lecture, gone. It's one of those things that we're going to talk about a very specific case, Euler-Bernoulli beams. So one of the things I want you guys to keep in mind as we're going through is we're making a lot of assumptions. And I want you guys to think about if those assumptions are okay. All right? So we're going to start off. Euler-Bernoulli beams. You guys have heard about it a lot. And if you guys look at your actual design courses, it's all based around this. Steel design, based around this. Concrete, same thing. Timber, masonry, aluminum, you name it, it's based around this. But we're going to keep in mind that there are assumptions, right? There's going to be assumptions. So let's jump in. Euler-Bernoulli beams. Beams are a very common topic in engineering. It's because it accounts for almost everything. We typically think of a beam as running horizontal, right? Makes sense? But is a column just a sideways beam? Yes. You could design a whole steel structure if you know beams. You got the columns to resist axial load. You got the beam above to resist axial load. And if I have any lateral loads, I can start putting beams diagonal. I can design a whole steel structure using just beams. Have you guys seen a steel structure under construction? It's just a bunch of beams. That's it, that's all. So if I know beams, I'm usually pretty good to go. Now, when we design beams, we have some particular interests in mind. In 374, what are two of the checks that are not related to instability that you guys do? What do you design for? Shear and bending moment. Shear force, bending moment. You have to make sure that the shear resistance and the moment resistance of our materials is greater than the loads applied. That's design 101. You make sure that those two are good. For steel, what's usually governing? Which one of these two for steel? Shear or moment? Moment. As you guys will see, steel is pretty good in shear compared to moment. If you guys have a steel beam that can resist the moment, it's very likely that it can also resist the shear. So when you do steel design, it's usually checking the moment and then just verifying that the shear is okay. What about concrete? What do you think is more limiting in concrete? Shear or moment? It's actually shear. Shear is crazy in concrete. Concrete breaks rather simply. Think about steel. Have you guys ever played with a piece of steel? Heavy, heavy, heavy. There's no way you can try and rip it apart. Concrete, its tensile behavior is terrible. If I want to shear through it, remember, shearing is cutting through it. If I want to cut through steel, that's a tough job. If I want to pull concrete apart, well, it has no tensile capacity. It's actually not too hard to do. That's why in concrete, we have to have a lot of stirrups to support the shear. Concrete design is very different than steel design. You take your moment and you place your longitudinal steel to resist it. Then you find your shear, and then you place your vertical steel to resist that. A whole different ballgame. But the key thing is that this right here is about strength. It's about strength. What is the other thing we have to design for? We have strength, but we also have, you got the ULS, ultimate limit states, and what's the other limit state? Serviceability limit state. What is that based around? Deflections. Again, you got to make things comfortable for the occupants. If I was, or let's say that there's people walking here and the roof was going like this the whole time, well, no one wants that. So the other thing that we're also very interested in is going to be deflection, which is going to be kind of the key here, deflection. To determine this deflection, we are going to assume Euler-Bernoulli beams. So what you guys are going to see is Euler-Bernoulli beams are going to be related to some very key assumptions. Now, depending on which literature you read or whoever's teaching the course, the assumptions are going to differ, but they're essentially all the same. For me, I like to list 4 of them. The first one is the deformations are small. You guys are civil. Is that a pretty valid assumption? Yeah. I don't want this beam deflecting a lot. It's what? 30 meters long? I'm not good at distances, but it's very long. But what do you think the deflection we're allowed in that beam is? Maybe 10 millimeters? Centimeters? Not a lot compared to its actual span. So deformations are small. Well, for our purposes, yeah, that's pretty good. The second one is the beam is made up of a linear elastic isotropic material. Is that true for steel? Is that true for concrete? Ooh, it's not. But here's the key thing. Here's the beautiful thing. Why do we have 2 limit states? Why do we have the ultimate limit states and the service limit state? This would be a great 374 question. I should go tell Eman-Por to put it on your midterm. Why do we have the 2 limit states? What's the key difference between those limit states? Determine if it will fail, but when you're calculating the loads, is that where things start to differ? Exactly. So in the service limit state, it's designed for everyday use. If I were to design deflection against the ultimate load, that's going to be very hard, because remember, at the ultimate limit state, if this beam were to fail, we want it to have lots of deflection. We want to see it coming down so we can get out. That would be overkill designing for the ultimate limit state. So we say, okay, for deflection, which again is serviceability, everyday use, we design for everyday loads. Under everyday loads is most of our materials elastic. Yes, we design concrete to break and steel to yield at the ultimate limit state, but we don't design it to break at service. Service is usually elastic. We don't want things breaking under everyday use. If you guys were just sitting here right now and the floor starts to crack, that's very concerning. So that's why this assumption is also pretty good. The third one, effects of Poisson's ratio are ignored. I already mentioned that. And then the fourth one, which is the one you guys probably see most in your design classes, is that plane sections remain plane. Now, I'm listing them here, and I'm going to show you in the derivation where each one of these comes into play. The derivation relies upon all 4 of these, okay? So let's go through the derivation. We're going to start at the very beginning. Shear and bending moment. This is coming straight from statics. Is there a relationship between my distributed load and shear? You guys remember? Yes. Is there a relationship between shear and moment? Yeah. So let's start at the very basics. To do that, we look at a simple infinitesimal slice. It's going to have a width dx, and it's going to be under a distributed load. So this would come right from the beam. So if I were to take a slice from the beam, or in other words, I cut my beam, should there be internal forces? Yes. So say, okay, I have an axial force N, And on the other side, I have the axial force plus the change in the axial force over this length. I have a shear force V, and on the other side, I have V plus the change in V over the length. And then, of course, we have bending moment. So we have moment on this side, and then we have moment plus the change in moment. One key thing to keep in mind in these derivations, and these come from the most purest form, so they're not really design friendly, they're more theoretical. We have Q going upwards, okay? Something to keep in mind right now at least. So say, okay, I now have what essentially is a free body diagram. Should this be in equilibrium? Yes. What happens if it's not in equilibrium? Exactly, it's moving and fly away. I thought, okay, I have a little bit of free time, so I went to Carlos's lecture. You guys know Dr. Logo, Carlos? I went to his Eng 130 lecture, and he had the perfect example of this. There was a guy who had a big steel beam, and he thought, oh, I'm going to cut it. So he takes his blowtorch, he's going down, and as soon as he cuts it, the beam flew up and hit him in the face. Of course, Carlos loved it because it's nice and funny. But the beam flew up. That was what happens when you cut the beam. You release internal forces, and that shear force pops it up. So it's one of those really fun things to keep in mind, that if I were to actually cut something in real life, it will move. It'll come back to rest, but it will pop up, which is quite crazy. So force equilibrium, if I were to take the sum of the forces in the x2 or the vertical direction, I get V minus V plus the change in shear plus Q times dx1, and in order to be equilibrium, it's equal to 0. Do these two V's cancel out? Can I just cancel those two V's? V minus V, is that a problem? No one has a problem? Perfect. So those are going bye-bye. Then we're left with this. We have the change in V times dx1 is equal to Q times dx1. I have dx1 on both sides, so can I just get rid of it? Yes. So I'm left with my first relationship. My distributed load Q is equal to the change in shear with respect to x1. This comes right from engineering 130 or engineering statics, whatever you guys call it. Now, in engineering statics, because let's be honest, first years aren't really good with theory, we simplify it for them. We give them negative Q is equal to the change in shear with respect to x1, and that's because in the actual theory, everything is derived with Q going upwards, but Eng 130 kids don't know that. So we usually put it downwards to make it more reflective of real life, but in the essential form, this is what we have. So Q is the change in shear with respect to x1. That's not too bad. And now we have a load shear relationship. What about moment? Can I get my shear moment relationship from this diagram? I'm seeing some nodding. What would I do, or what kind of equilibrium would I look at to find that? I took summation of the forces in the vertical direction. What would I do to find my moment relationship? What do you guys think? Summation of what? Moments. Come on, guys. There's three options: horizontal, vertical, or moment. If you're doing the horizontal, well, you're not going to come out with too much, really. So we're going to take the summation of moments. Now, it gets a little bit worse because our shear forces, if we were to take the moment about A, our shear over here does create a moment. Now, there is some simplification. We have negative M plus M. So do those cancel? Yes, those cancel, and I'm left with this. So what's the next step that we usually do? This follows almost the identical procedure that we did for Cauchy stress. What would we do next? dx1, dx1, dx1. Can I start getting rid of dx1? Yes. I can get rid of dx1 mostly. Because if you look at this one right here, it's dx1 squared. So even after I get rid of dx1, I still have dx1. How can I get rid of that dx1 now? We did the same thing for Cauchy stress. What do you guys think? Who remembers?
Take the limit.
Take the limit. Remember, when I'm analyzing this slice of the beam, I want it to be as thin as possible. So I take the limit as the x1 approaches 0. So I'm left with the shear is equal to the change in moment with respect to x1. So these two relationships come directly from Eng 130. But now we're going to take it a step further. In Eng 130, did we do deflections? No. Why didn't we do deflections? We said everything was rigid. Rigid things don't deform. We said it was all rigid. If things are rigid, does this change my equations? Ooh, that's where it starts to get fun. Let's put it this way. You guys will see that the rigidity of an object will start to change things. When it comes to determinate structures, determinants, things you can solve using equilibrium, it doesn't. You guys are taking 372 or have taken 372. How do you solve indeterminate systems? What do you look at? I'm seeing a lot of, and that's about right. But you start to look at the stiffnesses of objects. The stiffnesses of objects. Objects that are stiffer take on more load. That's how you start solving indeterminate structures. For example, if I was to solve an indeterminate truss structure, I use equilibrium, but I also use the cross-sectional stiffness of each of the truss members. I'm not sure if you guys are there yet, but you'll see it a little bit later. So we have these two relationships. Now let's figure out displacement. So this is when all the assumptions are going to start coming into play. We're dealing with beams. So the first thing I'm going to do is I'm just going to draw a beam. And then I have to define a coordinate system. So this is where the first kind of key piece of information comes into play. We say that our x2 axis is aligned with the left edge of the beam, and it goes vertical. And the x1 axis goes through the centroid of the beam. All right, there's the key. It goes through the centroid, x1. We keep it at the centroid because it'll lead to a lot of simplification later. Take this for instance. Let's say that the bottom of the beam was 0 and this was 1. All right, bottom of the beam was 0 and this was 1. What we're going to end up doing is a lot of integration. If I were to have my axis at the bottom of the beam, my integration limits would be from 0 to 1, right? 0 to 1. If I were to have my axis through the centroid, my integration limits are now negative 0.5 to 0.5. You guys remember in math, if you had a symmetric function and you're integrating on both sides, things become easier? Well, that's essentially why we keep it running through the centroid in this particular case. So here's the first two. Now, what we're going to do is we're going to look at the beam as it deforms. So this is where the assumptions come into play. The first one is plane sections remain plane. What does that mean? Plane sections remain plane. Not coming out of the page a little bit. That's a different assumption. What it essentially means is that this cross-sectional slice is going to stay straight. So notice how here my cross-sectional slice is straight and here it's also straight. That's the key. In reality, do you think it actually remains straight? No. For Euler-Bernoulli beam assumption, that's what we're assuming, and that's what we're doing here. I did here as an example, but it could be the same for over here. Let's say this cross-section right here, which is vertical. If I were to look at it on the deformed shape, it should also be straight. That's kind of the first assumption. So what we're going to do is we are going to say that the displacement of the centroids is y. So originally our point was here, it moved up to here, and that displacement is going to be y. To actually analyze this, we are going to look at 2 points. And I picked the corner point because it is the easiest. Now, another thing about plane sections remain plane is this. My neutral axis, if I were to extend it upward, it's going to be aligned the same vertically. So notice how my neutral axis in my undeformed configuration is at the same horizontal distance as my neutral axis in the deformed configuration. That's another key. Plane sections remain plane. My neutral axis horizontal location does not change. So what we're going to do is we are going to analyze kind of what's going on over in the top. So in the top, if this was an original thickness, x2, we know that this distance here is x2, and we know that it is rotated by an angle theta. Do we know what theta is yet? No, we just know that it rotated, so there is an angle. If I have a right triangle and I have x2, can I find the two components? If I know the angle and I know the hypotenuse of the triangle, yes. So that's all I'm going to do. This component, the horizontal component, is x2 times sine theta, and the vertical component is x2 times cosine theta. And this is what we are going to use to derive our Euler-Bernoulli beams. So what I can do is I can create position functions. This is where it all begins. Remember, in order to start getting strain and stress, we start off with these functions. For an Euler-Bernoulli beam, this is my position function. Clayton, how did you get that? Well, all it is looking at the position of these 2 points. If I want the position function for x1, which is horizontal, well, we know that our point started off at x1, so this dashed line, that's x1. So from here, all the way over to the dashed line, x1. Now, we know that this point here, it's not at the dashed line. It's a little bit back. So all we have to do is we have to subtract that horizontal component, x2 times sine theta. Does that make sense to you guys, where I got this component? Hoping so. The second component, the vertical, is going to be y plus x2 times cosine theta. Again, Clayton, where did you get that? Well, basically, from here, the centroid to here, this distance is going to be y, because we defined it as such. And then we have that additional component, x2 times cosine theta. So basically, we went from here to here as y, and then we came up a little bit more with that x2 times cosine theta. Now, x3 is just going to be x3. We're not actually accounting for any change in the x3 direction. So that's going to be my position functions. Right now, we've made one assumption. Plane sections remain plane. Again, it means that this is going to stay straight. It's not going to deform. And our neutral axis doesn't change horizontally. Now we're going to go into the second assumption. Small deformation. Small deformation. What can I do with sine theta and cosine theta if I assume small deformation? Is there simplifications to be made? Yes. So small deformation, this essentially means that cosine of theta is approximately 1, and sine of theta is approximately just equal to theta. So this is going to be my new position function. Again, sine of theta, approximately theta, and cosine of theta is approximately 1. So we just got x2. Now I got position functions. But again, the name of the game is I want strain. Can I get strain from position functions directly? Or do I need a different type of function? If I'm looking for my strain tensor, I need my displacement gradient. Does that come from position or displacement functions? Displacement. So this is a good start, and this comes directly from our diagram. But what I want are these displacement functions. This is how I'm going to start getting strain. So u is equal to x minus x, same as before. So all we're doing is we're taking this component, subtracting this component, and we get this. Our displacement functions are negative x2 times theta. Our y displacement is simply just y. And then we have no displacement into the page. Can I start finding my strain tensor now that I have this? Yes, and that's exactly what we are going to do. The last simplification, or not simplification because this is kind of known, is that the angle is simply the derivative of displacement with respect to x1. This came from Civi 270. You guys should have seen this in Civi 270. So this is a nice relationship. So basically, we have negative x2 times the first derivative of displacement with respect to x1. So we can find strains. We know our displacement functions, we can find our displacement gradient. So all I need to do is take this, substitute it into my Navali-U or displacement gradient equation to get it. Now here's the last thing that we need to kind of intuitively see. I'm taking derivatives, right? I'm taking derivatives. So is it important to know what things are a function of? Yes. Is my displacement over the length of a cantilever beam going to be the same? Is the displacement going to be the same at every point? No. It changes. If this was my beam, and let's say this was the 610, and I have a load, we know that the displacement changes over the length of the beam, right? Makes sense? So one of the things you have to keep in mind is that this y here, the displacement, it's a function of x1, or it's a function of the length of the beam. It starts to change. That's going to become important when we take derivatives. So once we take the derivatives, we get the following. We get negative x, or negative x2, times the second derivative of y. That comes from just taking this with respect to x1. Our next component, derivative of u1 with respect to x2. Well, we have an x2, so we get this. The rest are zeros, and then we have the derivative of y with respect to x1. Again, that comes from knowing that y has to be a function of x1. So this is our displacement gradient. From there, we can find our small strain tensor quite simply because we have a nice formula for it. You guys take that and substitute it into here. This is our strain tensor. This is when I started, I said, do you think it's going to be messy? No, because we made all those nice assumptions. For an Euler-Bernoulli beam, which again you guys use all the time in design, this is the strains. Is there shear strain? Is there strain along the vertical direction? There's one strain component. That's right here. Negative x2 times the second derivative of our displacement function. If I know the displacement of a beam, can I find the strain? Yes. The thing to keep in mind is this term right here, x2. This means that the strain is going to change over the height of my beam, right? It's going to change over the height. Do you guys see that in actual design? Does the strain change over the height of the beam? For instance, is the top in compression and the bottom in tension? Now you guys know exactly where that comes from. If I were to look at a specific section of the beam, let's say the midspan right here, that's at a very specific location of x1. So x1 is constant. If we were to know that x1 is constant, you guys will see that the strain profile is linear. Is that what you assume in design? A linear strain profile? Now you guys know exactly where it comes from. This is when you came in here as children and you're leaving as adults. Congratulations. With this right here, it seems so trivial. It's just one term. I can design almost everything with that. Isn't that crazy? Because if I know the strains, do I know the stresses? If I know the stresses on a cross-section, can I find the forces on a cross-section? If I know the forces on a cross-section, can I find the moment resistance? Yes. It's absolutely wonderful. So this is going to be the strain component. And now this is nice because for Euler-Bernoulli beams, this is it. I'm going to give you a question in your final. What are the 6 strain components of Euler-Bernoulli beams? And you guys thinking, oh, what a jackass. He wants 6 components? Is it really that bad? 0, 0, 0, 0, 0. It's only really one of them that you guys actually need to do. It's great. Aren't you guys liking this? I know that you guys don't care about the design implications, but for you guys, all you're thinking is, hey, this is easy. That's all I need you guys to think. This is easy. So this is the strain. If I know strain, can I find stresses? Yes. So that's what we're going to do. We're saying, okay, I now know the strains of an Euler-Bernoulli beam. Can I find the stresses of an Euler-Bernoulli beam? Well, yes. So what we're doing is we're taking those last 2 assumptions. Isotropic material, which gives us that nice relationship between stress and strain, and we're ignoring Poisson's ratio. So if that's the 2 cases, well, it turns out the stress-strain relationship isn't even what we covered in this class. It is, but it's more simple. It's just Hooke's law. If we're ignoring Poisson effects, our stress-strain relationship is just E times epsilon. We now know what epsilon is. We derived it in the previous slide. So our stresses are equal to E multiplied by negative x2 multiplied by the second derivative of displacement. Now I'm going to take that a step further. And this is where I might scare you guys. Oh, what happened? We're going to cover this in the next slide, but your formula for stresses is actually negative moment times x2 divided by I. Once you guys go to 474, actually, let's put it this way. Who's going to take 474? Where are my brave kids at? All right, I got a couple. That's concrete design. The whole first part of concrete is the service limit state, service. Under the service limit state, things are elastic. And your first assignment, I promise you guys, I was a part of it. I created it. Find the stresses at different points along my concrete beam. All right, so if I give you a cross section, first question, what is the stress at the top? Second question, what is the stress at the bottom? This is the formula you will use. Because if I know at a specific point, can I find the moment at a specific point? Yes, that just comes from statics. The moment of inertia of a beam, can I find that? Yes. So how do I find it at different locations? Well, it's just going to be different locations of x2. That's it. Your first 474 assignment, you guys will use this a ton. So and again, I'll show you how I got this in the next slide. So that's sigma 1,1. Am I good for stresses? Think about, yes, question.
That moment of inertia, if it wasn't a symmetrical shape, would you be using a strong axis?
If it wasn't symmetrical shape, yeah, so it depends what axis you're taking it on. This is assuming just plain bending, so it'll always be the bending axis. Yeah. So we have sigma 1,1. That was a great question. I don't think about it too much. So that's sigma 1,1. What was our shear strain? Shear strain from the previous slide. We said that we had epsilon 1,1. What were our other strain components? 0. So what do you think our shear stress is going to be?
0.
Who thinks it's going to be 0? All right. Who thinks it's not going to be 0? Thank you for the 2 people that voted. The answer is it's not going to be 0. What? How's it not 0, Clayton? This comes from the assumptions that we start to have. But the most simplistic way I can show you guys that there is shear is if I have a cantilever beam, I were to fix this end, and I were to put a distributed load. And I ask you guys for the bending moment function. Can you find it? Of course. Is there also a shear force function? Is there shear in my beam? Yes. So there is shear that comes directly from the applied load. So we have a sigma 1,2. So sigma 1,2 from mechanics, so this comes from 270, is equal to negative BQ divided by I times B. This will be the only part of Euler-Bernoulli beams that kind of looks a little bit gross, just a little bit, but it's not too bad. V, that's going to be our shear force function. So if I ask you guys for sigma 1,2 at the end of the beam, well, this is just going to be the shear at the end of the beam. If I were to ask you guys, well, what is I? Moment of inertia. If I were to ask you what is B, that is the thickness of the beam into the page. The only thing that you guys may not remember, but you have learned from 270, is Q, where Q is our moment of area, which is the second derivative. So I'm not going to test you guys on Q, don't worry about that. For a rectangular cross section, this is Q. All right, so you got the thickness into the page, which is B, and you got T, which is the height of the beam. So it's based on the cross section. Won't test you guys on Q. You just have to learn how to substitute it in. So now we can actually start getting into the actual juice. The actual juice of the course. Moment deflection relationships. We can begin to relate everything by looking or by determining the moments of a cross section. The moments of a cross section in its theoretical form is the double integral of negative sigma 2,2 times x2, and then with respect to basically the cross section. If I were to double integrate the cross section, what am I essentially getting? If I were to take a square and integrate it horizontally and vertically, what have I determined? Area. All this formula is stress times area, which is equal to what? Force times the distance. Force times distance, moment. So if we were to do this, and we now know that sigma 1,1 has the following form from the previous slide, well, we can say, okay, it can simplify to this. Whoa, Cleve, hold on. How did I go from here to here? I'm integrating over my cross-section. Does my elastic modulus change over my cross-section? No, it's constant. Therefore, I took it out. If I'm looking, again, just at a cross-section, one slice, does my displacement of my cross-section change? No. Again, that goes back to plane sections remain plane. My displacement doesn't change. So this is constant. I can take this out. x2, well, that's going to be a function of my cross-section, so I get this. Now, if you were to look at this equation right here and go back to inch 130, that's the definition of your moment of inertia I. So what happens is our moment is actually related to our deflection. M is equal to EI times the second derivative of deflection. And now we're saying, well, hold on. Do we have a relationship between moment and our applied load, Q? Yes. We know that Q is the derivative of shear, which is the second derivative of moment, which now, since we have an expression for moment, is the second derivative of this. We get this right here. This is the meat and potatoes of Euler-Bernoulli beams, right here. On your assignments this week, as you guys see in the seminar, this is what we're solving. Let's look at this equation. Have a lot of fun. Q. Do you guys know Q in typical questions? Or applied load? In real life, when I'm designing a beam, do I know Q? Yeah. E. Elastic modulus. Again, if I'm designing a beam in real life and I choose steel, do I know what E is? If I choose my steel section, do I know what I is? My only unknown in this equation is displacement. So this is where all the fun begins, all the fun. If I know my loading and what type of beam I have, can I solve for displacement? Can I solve for displacement? Yes. If I know my displacement, can I solve for moment? Can I solve for shear? If I now know moment and shear, can I solve for my stresses? Sigma 1,1 and sigma 1,2? Yes. This is where all the fun begins. Euler-Bernoulli beam analysis. So this is what you guys will be doing in this course. 3 steps. Determine the deflection from the applied loading. So we have a differential equation. You guys need to solve for displacement. Differential equation. Fourth order is as the fourth. How many boundary conditions are we going to need? What do you guys think? 4, exactly. If I have a beam that's fixed on 2 ends, what are the 2 displacements? If it's fixed. So there's 2 boundary conditions. What are the rotations at the end? There's 2 more. If I had a cantilever beam, what is my displacement and rotation at this end? 0. And this is a free end in cantilever. What are my moment and shear? What are the moment and shear at the end of a beam that doesn't have a support reaction? 0. So no matter what scenario we have, we can easily solve this. Isn't that crazy? Think about it. A fixed beam, fixed. Could you guys solve that in inch 130? No. You guys are learning how to solve it right now in 272. In this class, all you need to do is take this equation, specify the boundary conditions, you're good to go. It's very, very simple. So then we can solve for displacement. That's the key. Once we have displacement, everything else is gravy. With displacement, we can find moment and we can find shear. It's EI times the second derivative and EI times the third derivative. We can take it a step further and say, okay, if I now know M and I know V, well, sigma 1,1 is M times x2 over I. Well, I have M. x2 is x2. I have I. Good to go. Same thing for shear. I have V. Q is kind of more or less calculated, not a constant, but calculated. IV, just properties of cross-section. Now, the thing to keep in mind is this. Moment and shear change over the length of the beam. but they don't change over the cross-section. Is my shear at the top of my cross-section going to be different than the shear at the bottom? No, same thing for moment. Function of x1. Do my stresses change over the height of my cross-section? What do you guys think? Think about design. At the top of the beam, you have compression, bottom, you have tension. Are those different stresses? Yes. So these are a function of x1 and x2, as you guys will see. Because moment and shear, they're going to have the x1. Right here, we have x2 to make it a function of x2. And q is a function of x2, which makes it a function of x2. So that is Euler-Bernoulli beams. Is there any questions? Do you guys feel enlightened today? Yes. Thank you for the one nod. I appreciate it. So this is all you guys are going to be doing in your assignment. It's just going to be Mathematica. D-solve, define displacement, and then just throw all the rest in. Easy. So let's go do some fun examples. I put these on where I put the lecture notes. So hopefully you guys saw that. That was a great suggestion from the USRI, so I appreciate that. If you guys have more suggestions, let me know. I'm happy to accommodate. So we're going to look at this right here. The image below shows an I-beam. Do we actually call it an I-beam? This came from Sandler. What is an I-beam called in structural analysis? What kind of shape? What does the W stand for? You guys are good. That was overloaded, whose deformations violated the following assumptions. Now, if I were to look at this, how do you guys think this was overloaded? What do you think would cause that right there? Notice that was right at the corners, where it intersects the column. Shear, but sorry, I'm saying what kind of event? Chances are that was probably an earthquake. It's probably an earthquake. All right, so it says that this beam right here violates the following assumptions. A, plane sections remain plane. Do you think that section's remaining plane? No. So of course, this one has been absolutely violated. Linear elasticity. That thing elastic still? Absolutely not. Violated. Small deformation. I'll give you a hint. If you can see the deformation in a piece of steel, it's not small anymore. So I'll just give you guys, that is definitely violated. So this one would be all of the above. But this goes back to my thing that I like to tell you guys about design. We design a lot using Euler-Bernoulli beams. I asked you guys, keep track of the assumptions. Do you think realistically members behave as Euler-Bernoulli beams? What do you think? Clayton, if I were to design this beam above me and I assumed Euler-Bernoulli beam, just like the code book says, am I fine? Who thinks yes? Who thinks no? The answer is yes and no. When we derived Euler-Bernoulli beams, what kind of load did we have on our beam? Distributed load. In the midsection of this beam, is it just a distributed load? Yes. So it's good. At the supports, are there concentrated reaction forces? Was Euler-Bernoulli beam derived using concentrated forces? No. So that's where things differ. If you guys use Euler-Bernoulli beam to design the whole thing, this is good to go. I'm not kidding. I've done tests. I didn't believe it myself. I designed something as an Euler-Bernoulli beam, and I got, let's say, 50 kilonewtons. I went to the lab and tested it, or kilonewton meters. I tested it experimentally. I got 50.1. It's completely valid. The only time it is not valid is when you have concentrated loads. So if I were to say, okay, this is a concrete beam, design it as an Euler-Bernoulli beam, you can. This whole span is good. The only time where you have to start being careful is around supports, or if there's a concentrated load. Other than that, Euler-Bernoulli beams, good to go for design. Only concentrated loads. Look back at this picture. Is this part over here good to go? Yes. Notice how it's just around those concentrated loads. That's where it starts to get fun. All right, let's do another one. Gusset plates are used throughout steel structures to enforce cross sections. These gusset plates ensure a reduction of stress concentration. So you guys know what a gossip plate is? Kind of. Basically what happens is we have a steel beam, steel cross section, and what we do is we weld gossip plates, and there's a bunch of different types. So this is just going to be the one that I show. But basically we weld it like this. The purpose of these, and this is going to answer some of the questions, is to help the flow of stresses. If I didn't have my gossip plate, all right, I didn't. My stresses that I apply at the very end, so let's say it's under loading, my stresses would have to kind of come like this. Now, the problem with this is that we have a sharp corner. Fun fact, what is the stress at a corner of an object? What do you guys think? This is something I have to talk about a lot in finite elements. The stress at the corner of an object. Theoretically infinite. And you can see it all the time. You know, if you have the corner of something, how easy it breaks. Always. No matter what you have, concrete, whatever. That's why. Another fun fact, CN Tower. CN Tower, you guys should know what that is. Hopefully. The foundation of it at the base is round. The edges are rounded because you can't have an actual corner. Too much stress concentration. So what the gossip plate does, instead of going for that crazy one, it allows us to distribute stress a lot easier. So what happens typically in steel, it's very rare, but if you fail shear, and you don't want to use a thicker cross section, you can add in these gossip plates. These gossip plates also help with web crimpling. So one of the instabilities you guys will see if you apply too much stress is the web will kind of buckle right around there. These gossip plates will also help prevent that. And you'll learn a lot about them because we use them in this particular case. So it didn't really specify, but this right here is a moment connection. Moment connection. What happens is, in a moment, this flange at the bottom is going to want to pull out, and the flange at the top is going to want to go in. So what this does is this reinforces the web, so that when this beam tries to pull that web out, this provides additional stiffness to kind of keep it anchored. And the same thing above, which wasn't really shown. All right, enough structural design. What do these gossip plates do? Do you think that they reduce stress concentrations? Yes or no? Yes. Do they ensure that plane sections remain plane? Yes. Do they help ensure small deformations? Yes. So the answer is all of the above. All right, so let's go into the fun one. Consider the shown cantilever beam with the distributed load. The beam is supported at the end, and the boundary conditions are blah, 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 blah. I'm just going to go down to the fun. We got 5 points, or I guess 6 points. And we're going to skip the von Mises right now, and we're going to go right into this. Maximum sigma 1,1. What is the formula for sigma 1,1? Do you guys remember? Sigma 1,1 is equal to nothing. Negative m times x2 divided by I. So what we're going to do is we're going to look at our beam, which has those points, A, B, F, C, D, E. Where do you think our maximum positive sigma 1,1 happens? The first thing we have to do is look at the equation. Does I change throughout the beam? No, we're keeping it linear elastic. I is not going to change. So sigma 1,1 is going to be a function of two things, moment and x2. We have negative. In a cantilever beam, is our moment always going to be negative? Cantilever beam, moment always going to be negative. Yes. So the question becomes, okay, it doesn't really matter about the negative sign. What matters is we have moment and we have x2. So the location of maximum sigma 1,1 is going to be where my moment's the highest and where x2 is the highest. So if I look up here, where's my moment going to be highest? This side or this side? On the left. So we're left with A, B, and F. Come down here, A, B, and F. So I cancel these two. So now in our multiple choice, we have point A and we have point F. So we have A and F. The best way to kind of show you guys this, because x2 doesn't matter, is think about this. Positive x2. What does that mean? Tension or compression? Tension or compression? If I have a positive signal, tension. If this beam under this load is going to go downwards, is my tension going to be at the top or the bottom? Bottom. So what do you guys think? Is it going to be, or the tension should be at the top? You guys fooled me. I trusted you. F. What you guys will see is that for linear elastic beams, it's going to go something like this. Where we have forces that way, this way. What is my sigma at 0, or the neutral axis? 0. Best way to tell. At this neutral axis, what is x2? Oops, is it dead? No. At this axis right here, what is my x2 value? 0. If I come down and look at the equation, if x2 is 0, well then it has to be 0. Come down to the next one, the point of maximum shear. As you guys will see, sigma 1, 2, negative V times Q divided by IB. Now this one's fun because if you were to plot shear, and I'm going to plot it right here, you guys will see that shear is kind of a parabolic shape like this. So where's our maximum shear? At the ends or at the center? Center. So A, B, C, and D, those top and bottom points, we know that those are going to be eliminated. So A, oh actually let's see. A, F, E, and C. A, F, E, and C. I think these two. Point B and D, are those the only ones left? B and D, okay. So we established that the shear is going to be at the center. The question becomes, okay, is it going to be point B or point D? Over here or over here? What do you guys think? Who thinks it's B? Okay, who thinks it's D? Okay, you guys agree that it's B. Why? Exactly. If we look at this term here, we know that we're dealing with shear. The shear at the support is going to be much higher than the shear at the end. What is the shear at the end? 0. So there actually is no shear over there at all. So I forget which one this is. B. Where is it? Perfect. All right, so now we're going to go down and we're going to answer the last one. Von Mises stress. If we remember the theory, we only have 2 sigma components, 1, 1, and 3, 3. Or sorry, 1, 1, and 1, 2. Shear and normal, that's it. So our von Mises stress is going to be a function of both of them. It says, where is the maximum von Mises stress going to occur? Point A, point F, point E, or A and B. So basically, let's highlight them. Which color should we do? Green. Point A, so we have the bottom corner. Point F, so we have the top corner. And then we have point E. All right, so basically we have 2 corners. Let's start off with the easy one. If I were to compare the stresses at the support compared to the stresses at the end, which one do you guys think is going to be higher? This one, of course, because this is where all the moment is, and this is where all the shear is. The moment and shear at this end are 0. So then it comes, okay, what is the difference between these two? Remember, it's going to be a function of sigma 1, 1, and it's going to be a function of sigma 1, 2. Let's start off with 1, 2. What are my shear stresses at both of these ends? 0. So we know that von Mises stress is just going to be a function of sigma 1, 1 in this particular case. So what do you think it's going to be? Is it going to be F or is it going to be A? What's the difference between A and F in terms of sigma 1, 1. They should be the same value, but what? The sign. If this is in tension, this would be, let's say, positive 100. This is in compression, this will be negative 100. So basically, we have the same value, one positive, one negative. Question: does von Mises stress care about negatives? So do you think it's going to be all of the, or sorry, both A and B? Yes? Yes. It's going to be both A and B are correct. All right, and then the final one is, what is the positive value of sigma 1, 1? This is actually a very simple proof. Sigma 1, 1 is equal to negative m times x2 over I. The moment, and I'll go through this because I can hear you guys packing up, negative q times L over L over 2. So this right here is the moment. You guys can watch the video if you want a more in-depth explanation. x2, keep in mind that x2 is just the height of the beam, so it's going to be h over 2. And then the moment of inertia, in this particular case, is 1 over 12 base times height cubed. So if you simplify all this, you get 3 times q times L squared, all divided by base times height squared. All right. As you guys will see, these theoretical questions are not too bad. Even in the seminar this week, it's not too bad. Euler-Bernoulli beams. I'm hoping you guys learned something, and now when Eamon Poor or whoever else you have talks about it, you guys go, I know where that came from. Yes, question?
Is there a seminar next week?
Seminar next week? Yes, there is. I will not be teaching it though. Remember, this is my last kick of the can for seminars. I'm going to have my TAs take over starting next week. Everything's online though. Remember, assignment guides are your best friends. All right, thanks guys. I will see you guys on Tuesday next week.